Hey guys, Kenna here. Today we're going to go ahead and look at temperature, specific heat, and heat transfer. So it's important that we have kind of in our background the things we talked about before with respect to the kinetic molecular theory of matter and this idea of temperature actually being a measure of average internal kinetic energy for the material. And so when we start looking at specific heat, we're looking at the transfer of the thermal energy between molecules as it goes from one material to another or within that same material. And so we're going to look really at this process of heat transfer. Some of the terms will be familiar, although we'll look at them in very physics perspective. I'm talking about things like conduction, convection, radiation. But hopefully, by the time we're done, we'll have a really good understanding of what temperature is, how specific heat works, and what heat transfer is. So let's go ahead and take a look at our essential questions. Okay. Oop, too far. So, number one, what is temperature a measure of? What are we exactly looking at? And I kind of gave that to you already just with my little intro. But let's talk a little bit about how that works, and we'll relate that back to the kinetic molecular theory of matter. Number two, what different scales are used to provide units for temperature, and which one of these is the SI unit? So, in the United States, our primary unit you're probably familiar with. What is the unit primarily used around the world? And then lastly, which unit is actually used in science? Number three, how does a calorie relate to food and to energy? We talk about calories. You probably took this in wellness already. And so you have some idea of what a calorie is in general speak. But in terms of what we're talking about in physics, what is a calorie? Number four, what is specific heat? Now, this is a big term that we need to make sure we know how to do, and we'll take a look at how to calculate it. And what does it show you? Next one, can you differentiate between conduction, convection, and thermal radiation? These will be key terms in terms of how we deal with heat transfer. And then lastly, number six, that's bad grammar. What does thermal expansion measure? Okay, and you can probably get a good idea of that once you understand what thermal energy is and the relationship to temperature. Okay, so let's jump right in. There are two really commonly used temperature scales. The first of these is the Fahrenheit scale, and that's the one we typically use here in the United States. And if we compare it to water, water freezes at 32 degrees, boils at 212. You'll remember that from our warm-up sheets. There are 180 Fahrenheit degrees between the freezing and boiling point for water, and this scale is most commonly used here in the US. A comfortable room temperature for a Fahrenheit scale is somewhere between 68 and 72 degrees Fahrenheit. The Celsius scale, which is used in most other parts of the world, difference between water is 0 for freezing and 100 for boiling, so it's exactly 100 degrees. The Celsius scale is actually based on water. Now, most scientists and engineers prefer to use this because it's much simpler for a lot of what we experiment with. Most other countries in the world use this scale, including for their daily weather. So if you think about your weather app that's on your phone, yours probably reads in Fahrenheit, but if you were to go to almost any place else in the world, it would read in Celsius. So once again, just like last term when we were talking about unit conversions, we would need to be able to go ahead and convert between the American unit of Fahrenheit and the Celsius scale, which most of the rest of the world uses. How do we do that? Well, this process isn't that difficult. We have equations for this, and we can go ahead and figure it out. If you want to get Fahrenheit from Celsius, you take Celsius times 9/5, and then you add 32. If you're trying to get Celsius and you have Fahrenheit, you subtract 32 and times it by 5/9. Okay. Why does it matter? Why do we need to understand the difference between these scales? Because if we get a weather report that says 21 degrees Celsius in London, England, at first glance, if you're thinking Fahrenheit, you're going to think, oh man, that's horribly cold. Uh, but that's actually a pleasant day for shorts and a t shirt. Whereas a weather report from Minneapolis that predicts 21 degrees Fahrenheit is going to suggest to you that you need winter coat, gloves, and hats. So The scales are not set the same way because remember, freezing water is 0 in Celsius, 32 in Fahrenheit. Boiling water is 100 in Fahrenheit, 121. I mean, 100 in Celsius, 121 in Fahrenheit. So, what is temperature anyway? We have these units to measure it, Celsius and Fahrenheit, but what is it? Well, it's a measure of the average internal kinetic energy of the atoms. Okay. Don't confuse this with the motion of actual movement, like if something is moving forward in terms of our mechanics that we talked about last term. Atoms, remember, are always moving. Okay, whether it's the atoms in a solid material, which kind of just vibrate in place, or a liquid where they flow over each other, or a gas where they're moving in straight lines away from each other all the time. Okay. Each atom is free to move some amount. When the temperature goes up, the amount of motion increases, and the energy of the motion increases, and the atoms begin to jiggle more vigorously. Temperature does not increase when an object is moving, at least not noticeably. There is some friction, and that's a force acting upon the material, but that's a little different. So, how can it be a measure of kinetic energy is different than the kinetic energy that we talked about before? Because this is the average internal kinetic energy of the entire material. Okay. So, the random motion versus what we've seen in terms of a non-random motion or the movement of an actual object in terms of mechanics. Okay. And since the material as it sits there does not really move in most cases, it may slosh a little bit if there's some motion going around in the table or something. But um, what we're looking at is the actual movement of the particles inside that make up the atoms themselves. And this provides a certain amount of internal kinetic energy, which is what we measure in terms of temperature. So, temperature measures the kinetic energy per atom due to the random internal motion. What are those random motions? Well, they're scattered in all different directions. Remember that we're really looking at vectors here, and so they mostly cancel each other out. If it's purely random, the average change in position nets out to about 0. So again, remember vectors. And this is going to come in again if we go ahead and get time to talk about uh, magnetism, but we'll get there when we get there. So higher the temperature, the higher the random kinetic energy of each atom. So this is something you'll want to make sure you keep clear. In terms of the kinetic molecular theory, the higher the temperature, the higher the random kinetic energy of the atom. Hot atoms move faster than cold atoms. If you heat a rock with a torch long enough, the atoms get so much energy that they start to break away from each other and the rock will melt. If you keep heating the same liquid even more, it'll eventually get to a point where it begins to boil. And those atoms are able to go ahead and actually leave the intermolecular forces that hold them together from the liquid. And they begin to fly off into the atmosphere. And so this is an important concept to keep in mind is that when we're looking at temperature, we're looking at adding thermal energy and we're looking at changes in internal kinetic energy. Okay, again, internal random kinetic energy that's inside the actual atom. Okay, so that's what you really want to go ahead and focus on when you're thinking about temperature. Now, last class, we introduced you to the phases of matter and intermolecular forces. So as temperature changes, the balance between temperature and intermolecular forces changes. At temperatures below 0 Celsius, the intermolecular forces of water are strong enough to overcome temperature, and the water becomes a solid. On the other end of this, when you get above temperatures of 100 degrees Celsius, the kinetic energy is great enough to overcome most of those intermolecular forces, and the actual atoms start to fly away from the substance and turn into a gas. Now, most of the time when we measure temperature, what we're looking at is a thermometer. Okay, there are other tools that we can talk about as well, but most of the time we're using a temperature. Our skin can sense warmth and cold, but we're not very good at gradating that and going ahead and using an actual scale by touch. Uh, as such, we use the thermometer so that we can get a pretty consistent, unbiased reading. This allows us to quantify the amount of kinetic energy inside a particular sample. Most of the thermometers we use at school are going to be alcohol thermometers. I know a lot of people still think it's mercury, but they haven't used mercury in thermometers for a while. Okay, so they typically add color, some sort of food coloring, to the liquid alcohol as a gauge. And so what happens is as the temperature increases, the alcohol expands, remember expansion, and it rises up the tube. As the temperature decreases, the alcohol condenses, lowers down the tube. Now, this works due to the small change in volume for a very narrow tube. That's why you see a very thin line in terms of the actual alcohol inside the thermometer. There are other types of thermometers, and they may be based on things like electrical resistance. You think about a thermistor that used to be in cars, or chemical color changes. You think about the little sticker that's on the side of some of your fish tanks. Okay? So, temperature is a measure of thermal energy, and we can measure that by how much it makes the liquid inside the thermometer expand, heat increases, or contract, heat decreases. Now, there is a bottom to the thermometer, okay? And you can get the temperature to go down low enough, just as you can get the temperature to go up high enough that it actually can break the thermometer. Well, in nature, there is no real upper end. Okay, temperatures can keep going up as long as you apply thermal energy. We'll talk more about how this relates to the laws of thermodynamics next class. But for what we're also talking about, we also have to think about the low end and how low can it go? Well, in our minds, you get to zero, right? Well, okay, so in Fahrenheit, we definitely have negative degrees in temperature, and you have negative degrees in temperature for Celsius as well. But is there a point where all of this motion, this random motion we talk about for the kinetic molecular theory, stops? And the answer is, in theory, yes. This is what we call absolute zero. So while there may not be an upper end to how hot something can get, there can be a lower end for how cold matter can get. And as the temperature is reduced, the molecules begin to move more slowly and more slowly. And when the temperature actually gets to this absolute zero, molecules have the lowest energy they can ever have, and the temperature cannot get any lower. Now, if you remember the video we talked about before, when we were looking at millikelvin or nanokelvin, okay, these are temperatures approaching absolute zero, but we have never actually reached absolute zero where all motion stops. Okay, so technically speaking, as far as we are aware, molecules will never become absolutely motionless because the kinetic energy is so small. It's close. Those are those quantum jitters that we talked about, but it never reaches absolute zero. So, what is absolute zero? Well, it's about negative 273 degrees Celsius or negative 459 degrees Fahrenheit. That is cold. Okay. Even the temperature of outer space, which we think about as being one of the coldest things in the universe, is about 3 degrees warmer than that, okay, in terms of the Celsius scale. Fahrenheit, it's a little more than that. So you cannot have temperatures lower than absolute zero. All right, so one of the cool understandings of this as we've developed this is we've been able to develop what are known as superconductors. So I have a brief video here that's going to show how that works.
A superconductor is a metal that suddenly, below a certain critical temperature, spontaneously falls into a new state of matter. And this state of matter has a property that it conducts electricity perfectly. So it's a phase transition. It's like, going from liquid to solid. Water changes its state. Well, here it's the electrons that are changing their state from a sort of state where they're just doing their own thing individually to a state where they form pairs and enter a quantum coherent state and transmit electricity perfectly. So at the heart of that phase transition is this force that binds them together in pairs. And the stronger that force, the stronger the superconductivity, and the higher in temperature you could make it persist. And so we want to understand the force, where that force comes from. But the outcome, the upshot, the measurable evidence is that suddenly they conduct electricity perfectly with absolutely zero resistance. And I love that because it's rare that in life, in real life, you talk about perfect, infinite, perpetual motion. You know, these things are sound like dreams. Well, they're real when you come to superconductivity. Superconductivity has those magical properties, which do continue to fascinate people even 100 years down the road. Not just, people like me who are fascinated, but many people in the public, many young people are attracted to this subject because of that fascination.
So there's a lot of stuff we can talk about, and there are whole things about quantum mechanics that we can look at quantum computing in terms of how much data we can transfer or store. And so there are a whole bunch of fields. They've even started looking at computing using things like biological molecules that may not have any resistance in the same way we think of with electricity. But I digress. Okay. So in order to actually accurately measure with respect to absolute zero and the amount of thermal energy in any object, they needed to create a new scale. And they created that scale based on Celsius because remember, Celsius is nice and round, 100 degrees between freezing and boiling of water. So what you have is what's called the Kelvin scale. And so you'll notice that the unit down at the bottom, instead of having degrees C or degrees F for Celsius and Fahrenheit, it's just a K. Okay, and so K stands for Kelvin. And so these are the units that are preferred in terms of physics and chemistry with respect to temperature. Now, that being said, if we go back to our pressure temperature laws, our gas laws, pressure, temperature, volume, uh, these should be done in Kelvin. Okay. So the pressure of a gas depends on how fast the atoms are moving. The Kelvin scale is used because it measures the actual energy in the atoms relative to the Celsius scale in terms of thermal energy. We use our Kelvin units, and you would need to convert any Fahrenheit to Celsius before converting Celsius into Kelvin. But essentially, it is the Celsius scale plus 273.15. Okay. And so it's a pretty simple transition to go from Kelvin to Celsius because remember, Kelvin's based on Celsius. But Fahrenheit needs to go to Celsius in order to convert into Kelvin. Now, temperatures can go up, as I mentioned before, almost indefinitely. As the temperature increases, we get these exotic forms of matter, our different types of plasma. Uh, and we know that we've seen 10,000 degrees Celsius atoms start to come apart to become that plasma. In a plasma, the atoms themselves are broken apart into separate positive ions and negative electrons, and they flow around in kind of a soup. And it conducts electricity and is formed in lightning and inside the stars. But the low end is set at absolute zero. Okay. All right. So now we have an idea what temperature is, how it works. To change the temperature of a system, you have to add or subtract energy. So when it's cold outside, when you turn up the heat, what you're really doing is you're adding thermal energy to that particular space. Now, this is important to understand with respect to system and surroundings we talked to you about before. You know that adding heat increases temperature, but have you ever thought about exactly what heat is? And so this is that thermal energy. And so what you're doing is you're causing those random random motions inside the molecules to increase the temperature. Okay. And so heat flows naturally, and we'll talk about this in terms of our laws of thermodynamics, from one area where there is less motion to an area where there is more internal kinetic energy. Okay. So higher areas, warmer, move energy towards cooler areas, lower energy. When you heat up a pot of soup on an electric stove, let's say, that's what I have out in the kitchen. Uh, when you start trying to do that, your electrical energy is being converted into thermal energy as it goes through the stove. The thermal energy is related to temperature. And remember, temperature measures those random kinetic energy of these molecules or atoms. Thermal energy is the sum of all that kinetic energy of the atoms or molecules added up together. So the amount of thermal energy depends on the temperature, but also upon the amount of matter that you have. If you have a larger piece of matter, it's going to take longer to heat it up. So thermal energy includes the energy of all of the atoms inside a sample. So therefore, it depends on both mass and temperature. This should make some sense because it's easier to heat up a small room than it is to heat up a bigger room because there's more matter there that requires more energy to heat up the same amount. Now, this is something we can measure. There are three different units that are commonly used for heat and thermal energy. And this is because people did not realize heat was energy originally, and this took them some time to figure out. The metric unit for measuring heat is the joule. Shouldn't be too much of a surprise because this is the same joule that we use to measure energy. Now, a joule is not very much heat though. The average hair dryer puts out about 1200 joules of heat every second. In the United States, we tend to use the term calorie a lot. But a calorie is defined as the quantity of heat needed to increase the temperature of 1 gram of water by 1 degrees Celsius. So 1 calorie is equal to 4.186 joules. Okay? So originally, this was a scientific measurement used by nutritionists. The last unit, which you still find in a lot of heating and cooling units, if it's a air conditioner or if it's a space heater, and that's the BTU, or British Thermal Unit. Now, this unit is often used still, as I mentioned, in our air conditioning systems or in our space heaters. 1 BTU is equal to 1055 joules or 252 calories. All right. So now let's think about that term calorie because it's one I know you guys have done before in your wellness classes. You may have noticed that most food packages list calories per serving. Now, there's one key thing that you'll really want to pay attention to when you go ahead and do this. When we start talking about calories, take a look at this C. Okay. This C is capitalized. Okay. Calorie versus calorie. I know, same word, but that capital letter actually means something very different. Okay. The kilocalorie is what we mean when we say with a capital C. So this is actually a kilocalorie. And if you remember our prefixes, kilo means 1,000. So a calorie with a capital C means 1,000 calories. So if you buy a candy bar at the grocery store and it says it contains 210 calories, what it really contains is 210,000 calories because calorie with a capital C is used to represent a kilocalorie. Now, calories in our diet come from fat, proteins, carbohydrates, alcohol, all sorts of different things. Carbohydrates and proteins contain 4 calories per gram. Each gram of alcohol contains about 7 calories. Fat has a whopping 9 calories per gram. Again, notice those are all written with a capital C. If we consume more energy, or calories, than our body needs, the excess is stored as fat. So this ties back to your biological days when you were in biology and talking about your macromolecules. Do you remember your macromolecules? We have carbs, lipids, nucleic acids, proteins. Okay, all of these different macromolecules are built from organic molecules. But one of the things we pointed out in biology is that carbs and lipids are made up of the same stuff. CHO. And what they do is your body, if it doesn't use it, it reconfigures it and stores it as fat. Now, fat is a type of lipid, whereas carbohydrates are your sugars and starches. Okay. Body fat can be broken down later to provide energy to our bodies when we're short on food, but this takes a lot of work because that fat has to be converted back to a carbohydrate in terms of a starch or a sugar that can be then broken down further to be utilized to recharge the ATP in our systems. Okay, so when we start looking at calories, remember that this is actually a measure of energy in. Okay. And how your body uses that depends on your activity level, your sleep habits, different biological underlying factors, and what the composition of those calories are. But ultimately, at the baseline, it is energy, and energy in is going to equal energy out. All right. So, what we need to think about then is how does our body deal with temperature? Okay, we can talk a little bit about whether you sweat or whether you shiver when you're cold. But what we're looking at is what's happening in terms of the actual matter itself. If you add heat to an object, how much will its temperature go up? Remember that it's not just based on what it's made of, but also how much of that thing you have. So it's mass as well. If you double the mass of an object, you're going to heat up. You need twice as much energy to increase the temperature. The amount of temperature increase also depends on the kind of material you're heating, though. So it takes different amounts of energy to raise the temperature of different materials. Water versus steel versus iron versus rubber. It takes about 9 times more energy to raise the temperature of water by 1 degree Celsius than it does to raise the temperature of the same mass of steel by 1 degree Celsius. So, knowing how materials resist temperature change is important, and the term we use for this is specific heat. Specific heat tells us exactly how much heat is needed to raise the temperature of 1 kilogram of material by 1 degree Celsius. A larger specific heat means you have to put in a lot more energy for every degree increase in temperature. And specific heat is measured in joules per kilogram per degree Celsius. Okay? So, knowing the specific heat tells you how quickly the temperature of a material will change as it gains or loses energy. If it has a really low specific heat, like steel, then temperature will change relatively quickly because each degree of temperature change takes less energy lost or gained. If the specific heat is high, like water, then the temperature will change relatively slowly because each degree or change takes more energy gained or lost. And this can be expressed in the mathematical equation delta Q equals mc delta T. So, what do all those pieces mean? Well, Q represents the heat transfer to the material, how much energy in terms of heat is coming in, thermal energy. The M represents the mass of the material. The C is the specific heat value for that particular material. That would be different if you had steel versus water, etc. And delta T is the change in temperature. Okay? So you can use this equation to figure out how much energy it would take to heat a swimming pool or boil a liter of water. All right, and that's what your worksheet's going to be on today is looking at how to go ahead and utilize this particular equation. So why does specific heat vary? Why is steel different than water? Well, in general, materials made up of heavier atoms or molecules have a lower specific heat compared with materials made up of lighter ones. That may be counterintuitive at first, but this is because temperature measures the average internal kinetic energy per particle. Heavier particles means fewer particles per kilogram. Okay, so there are less molecules or less atoms inside a material made up of heavier particles than there are in something made up of lighter particles. Energy that is divided between fewer particles means more energy per particle and therefore more temperature change. So it's easier to heat up heavier molecules than it is to heat up lighter molecules because there are fewer molecules per kilogram. So then how is that energy transferred? Well, there are three different forms of transfer that we typically look at. These are conduction, convection, and thermal radiation. So let's look at each of these and better understand how these types of transfer work. So conduction is the transfer of heat by the direct contact um, between the particles of the matter. So I want to highlight that for you because that's a big piece here. If you're going to have conduction, you need to have direct contact. So they're touching. Okay. So let's go ahead and write touching just to remind ourselves. Convection, however, is the transfer of heat through the motion of fluids such as air or water. So if you actually were to go ahead and hold your hands above a campfire that you have when you're out camping in the summer, your hands warm up, not because they're touching the fire, but because that heat is being transferred through convection through the air to your hands. Okay? So that's convection. Now, the last one is a little tricky. So, thermal radiation is when heat is being transferred in the form of electromagnetic waves. And this includes light. And because remember, we can have these energy transformed in terms of energy changes that we talked about at the end of last term. So, thermal radiation comes from electromagnetic waves. And this is how our planet gets most of its energy in terms of the electromagnetic waves coming from the sun striking our atmosphere. Okay, so this one's a little trickier, but heat rises is going to be convection as it goes through fluids, right? Thermal radiation is a little different, and because it's using electromagnetic waves, this can be transferred through a vacuum or like the near vacuum of space. Now, I have some little short videos to kind of go over this in some detail, so hopefully you understand it better when we're finished. So I'll go ahead and get those started, so hopefully we can get there.
Conduction of heat. This video talks about the conduction of heat. Let's perform an activity to understand the conduction of heat. Take a straight and flat rod of aluminum or iron to fix some nails using wax. Fix the rod to a stand. Now, heat the other end of the rod with a spirit lamp. Absorb the order in which the nails drop down. The nail near the spirit lamp falls down first, followed by its nearest neighbor, and so on. The one near the stand falls down last. The heat supplied by the spirit lamp flows to the other end of the rod by conduction. We know that in solids, molecules are closely packed, touching one another. When heat is supplied to one end of the rod, the molecules absorb the heat and begin to vibrate vigorously. These vibrations are passed on to the neighboring molecules and make them also vibrate. This phenomenon is repeated throughout the length of the rod. In this way, the heat energy gets transferred from the hot region to the cold region. Transmission of heat in solid substances takes place through conduction. For the conduction to take place from the hot portion of the body to the cold part of it, or from the hot body to the cold body, the two parts should be in contact with each other. When the temperatures of these bodies are equal, the flow of heat through conduction process stops. We can observe this phenomenon while using a thermometer. When the bulb of the thermometer touches a hot substance, the mercury absorbs the heat and it expands. When the temperature of the tip of the thermometer and the substance are equal, no transfer of heat takes place. So, the level of mercury does not increase further. Two conditions are to be fulfilled to transfer heat from one object to another by conduction. They are: 1. The two objects must be touching each other. 2. There should be some difference in the temperature of the two objects. Heat transfers from the object at a high temperature to the other which is at a low temperature. When a teaspoon is put in a cup of hot water, these two conditions are fulfilled. Water and the spoon are touching each other. The temperatures are different. So the cold spoon absorbs the heat from the hot water, and so its temperature rises.
Okay, so again, it has to touch and there has to be some difference in the amount of thermal energy of the two bodies, what they call the hot body and the cool body. Okay, so now I want to talk a little bit about convection. One of the easiest ways to visualize this, because we deal with this a lot in things like earth science and when we're looking at meteorology and weather patterns, is what we call convection currents. Um, so I want to go ahead and show you a quick demonstration of convection currents so that you can hopefully better understand how heat energy, this thermal energy, flows through a system.
Take a deep breath. Get ready for one of the most hypnotic things you'll ever see in a science class.
He really sells it, doesn't he?
Have you heard that heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides.
This is true for
You can
gases
see it better
too.
from above. Watch that blue food coloring get drawn in. Do you see it? The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it. As it goes out to the edges, it starts to get cool, and cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are called convection currents, and you see them moving here in two big ovals. They're one of the major things that drive ocean currents, especially in the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe, some of them taking 1,000 years to complete their course. Understanding convection currents will help you get a grip on weather systems and the movement of Earth's continents over the eons, and even the workings of a lava lamp. If you want to try this for yourself, click on this link for all the directions you'll need. Thanks for watching.
Okay, so it's a pretty cool demonstration, and understanding how weather works and how ocean currents works is a valuable skill to go ahead and have. But here we're just using it as a demonstration to best understand how convection works and the flow of thermal energy, but also in terms of replacing the void and this concept of a system, okay, working together. The last topic we want to do is thermal radiation before we finish with thermal expansion and let you go for today. Now, thermal radiation is the trickier one, so pay close attention. And they're doing this in terms of a one-pager. And so if you want to recreate something similar to this, I think it might help you visualize just what thermal radiation is. Might be a good way to go ahead and do your notes for this section.
Thermal radiation is all about the transfer of thermal energy, or heat, from one place to another. It is one of three processes which do this, and the other ones are conduction and convection. So it's worth considering thermal radiation as a topic in the context of those other two topics as well. It's worth pointing out that thermal radiation is part of the electromagnetic spectrum, and in that context it's often referred to as infrared radiation, perhaps confusingly having these two terms, but these two are 100% exactly the same thing. Now, if you remember just one thing from this video, let it be this. if you have a black, a matte, or a dark surface, it will absorb and emit more than a white or a shiny or a silvered surface. I'm going to talk about this in more detail, but that statement really sums up this video, and it sums up the whole topic of thermal radiation. It's important to make clear also the difference between thermal energy and thermal radiation, because people often mix these two up, but they're quite different things. Now, to say that something is hot, that is to say that it has a lot of thermal energy. Now, that in turn means that it gives out a lot of thermal radiation. It's a little bit like a bright object, like a light bulb or a computer screen or the sun. Because it's bright, it gives out a lot of light. And in a similar way, a hot object will give out lots of thermal radiation. So the words bright and hot are properties of an object. They're ways of describing what an object is like, whereas light and thermal radiation are things that are given out by that object. Now, how hot something is not the only thing that affects how much thermal radiation it gives out. Perhaps strangely, the colour of an object also affects this. If we take a hot object, for instance, and paint two different colours on its surface, perhaps we paint one part black and another part white or silvered, then we know that these two coloured parts are at exactly the same temperature because they're part of the same hot object. However, it's possible to detect more thermal radiation coming from the darker surface than the lighter or more reflective one.
Now, I want to talk really briefly about this because in terms of trying to deflect a NEO or a near-Earth object streaming towards our planet, this has become a big topic of conversation. Is what happens if you were to paint a comet so that you have a light color on one side and a dark on the other? Because they emit different amounts of radiation, okay, and in turn also reflect different amounts of radiation, the decomposition of them are going to be different, which is going to change the shape and distribution of weight for that particular object. So there are a lot of applications of this type of understanding in terms of astronomy and cosmology. So just kind of keep that in the back of your mind.
Let's imagine a hot object of some kind. This might be the sun or a fire or the grill in your oven maybe. Because it's hot, it's giving out lots of thermal radiation. It might also be giving out light, such as, for instance, with the sun, but that actually does nothing at all to heat the objects up around it. It's only the thermal radiation that does this. If we put two surfaces at the same distance away from that object, so they're receiving the same amount of thermal radiation, a black surface will absorb more thermal radiation than a white surface, and that means that it will heat up more quickly. This is why it's a bad idea to wear black on a really hot day, or you'll stay cooler if you wear white. Well, thanks very much for watching. If you'd like to download a copy of this page of notes, or if you'd like any more information on any physics topics, please go to my website, atkinsonphysics.com. This is my first attempt at a tutorial video, so please let me know if you liked it, and also if you'd like me to cover any.
Okay, so I'll leave it at that. If you're interested, you can go check it out. But the last thing we really wanted to talk about briefly, and in terms of calculations, we're not going to do this as a calculation that we would do on a test, but it is good to understand how thermal expansion works. Have you ever driven across Ferry Street Bridge and noticed that there are these little kind of metal gaps in the bridge at the two ends? Well, the reason for that is actually for thermal expansion. As temperature increases, the kinetic energy and vibration of the molecules increases. We've got that. Well, these increased vibrations make the particles take up more space. This is expansion. Okay? Because of this, we don't want buckling of materials like roadways, railroads, and things like that. Because all solid materials will expand as their temperature increases. Some of them, like plastics, for example, expand a whole bunch. Others, like glass, expand only a little. So just like when we were talking about specific heat, the type of material is going to determine the amount of thermal expansion. Okay. If temperature decreases, it can also be affected by this concept of thermal expansion, but instead of expanding, it's going to contract. And we can predict how much it's going to expand or contract depending on what's called the coefficient of thermal expansion. So this describes, like specific heat describes how much the temperature changes, this describes how much the material expands for each degree in temperature change. Now, if you look very briefly at this table, again, you're not really going to be responsible for this. I just want you to understand the term. You can look at the fact that when we look at certain solids versus certain oils, we can look at how much expansion occurs. When you're looking at solids, you can see that's times 10 to the negative 6. When you look at a liquid, that's times 10 to the negative third. But we can start looking at the things like water has a lower coefficient of expansion than alcohol does. When you look at something like mercury, however, that's even lower than water. Okay, when you go ahead and start looking at some of our liquids, like our ether, that thermal expansion is higher. If you go over to your solids, you'll notice that we have aluminum, which has a very high thermal expansion coefficient when compared to something like quartz glass, which has a 1.5. All right. Why do we care? Well, for the longest time, there was a problem. Thermal expansion of long, continuous sections of railroad track was the driving force behind rail buckling. And you can see in these particular examples, when it got too hot, the railroad track was no longer straight, smooth, and you actually saw an increased number of trains derail due to this problem. It turns out that just between 1998 and 2002, there were 190 train derailments in the US alone as a result of railroad train buckling. Okay, this process could have easily been solved if there was some sort of expansion built into this. And so this is why you see, especially in newer bridges, these expansion gratings where they actually allow for the heating and cooling of the material that you're driving on. And the same thing is true for railroad tracks. Okay, and you'll see that they don't do as many of these long continuous pieces as they used to. They have a little bit more of these transitions, and that's why you hear the click, 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 click when you go ahead and ride a train. All right, so that's all I've got for you guys today. Stay safe, stay healthy, and we'll see you guys soon. Take care of yourselves. Bye-bye.